This is part 4 of lecture 12 of Applied Machine Learning. In this video, I am going to define a new tree-based algorithm that is going to be different from the decision tree that we saw earlier, but it's also going to use the decision tree as a building block. And the name of this algorithm is going to be the random forest. The random forest is going to be motivated by a problem that decision trees have, which is overfitting. And we saw previously one way to address overfitting, which is the bagging approach, in which given a data set X, a labeled data set of X and Y, we repeatedly sample random subsets of this data, and then we fit we fit the instances of the same, we run the same machine learning algorithm on each of these random subsets of the data to obtain a different predictive model, and then we add these models to an ensemble, and then at prediction time we return their average prediction. And even though each of these models may individually be overfitting the data, when they overfit the data, they will make errors outside the training set in random ways. And so if we average enough models, all these random overfitting errors should cancel out and give us a more stable prediction. We also saw earlier the decision tree algorithm. And one way to define the decision tree algorithm is that we have a set of rules which partition the feature space into a set of regions. Each region is denoted by R. And then when we have a new training instance, when we have a new input, we first see which region does X fall into, and then we predict we output the prediction for this particular region. And in practice, these regions are obtained by applying decision rules, which can be organized in a tree-like structure. So here is an example of a tree over two variables. Here, depending on whether x1 is greater or less than t1, we're going to the left or to the right. If we go to the right, then we have another rule. Then we go to the right again, we have another rule. And then we have these final two regions. In total, we have 5 regions in this decision tree. And this gives us a partition of the feature space, which looks like this grid. Now, let's investigate some properties of decision trees on a data set that we have seen earlier, which is the flower data set. Recall that in the flower data set, we have data for about 150 flowers. They for each flower, we have various measurements that have been taken here in centimeters. And we can visualize this data set, we can first look at the raw inputs, which is a data frame with 4 feature columns and a target. The target takes one of 3 possible values depending on what the class is. And we can visualize this data set in 2 dimensions by taking 2 of these dimensions and displaying each point as based on where it lands according to these 2 measurements. And you immediately see that you have clusters in the data. Here we have one type of flower in blue, which is different from all the other flowers. And then you also have 2 other classes, which are more similar to each other, but still different. And these are 3 types of iris flower. Each color here corresponds to a different type of iris flower. Let's see what happens if we train decision trees on this flower data set. I'm going to be reusing this code a lot, and this is just boilerplate code for visualizing decision boundaries and decision regions over this iris data set. So this is not really important to follow, but if you're interested in how we use matplotlib, you can later go and revisit these visualizations, but this is just boilerplate code to generate figures. Let's now train a decision tree on this data set and visualize it. Here I'm using the first 2 features from the data set. I create a decision tree classifier, which I've imported earlier from scikit-learn. I fit the data, I generate predictions, and then when I visualize them, I have this highly irregular region. So this is a visualization of the predictions from the training set. And you can see here that we do have these kinds of regions that we have defined earlier. So here, this yellow rectangle is a region. This also is a rectangle, which is a region. It has this, you can immediately see this partition of the feature space, of which I gave a toy example earlier. And each partition is colored, each region in this partition is colored with the class of the prediction that it's going to be making. So there are two immediate problems that you can see with that decision boundary. First is that it's highly non-smooth and blocky. It's fairly unlikely that, like the partition between these 2 points is a straight line, or here that it has this jagged structure and here is a straight line. It is probably some kind of line or curve here that is diagonal, and this tree can only represent these very blocky regions. That is one problem. But the bigger problem is that it clearly overfits the data. You can see here, for example, it has found this one brown point, and it has decided to draw this really big brown block in the middle of the 2 other classes, just to make sure that this is classified correctly. This is an example of overfitting, and here also it's learning a decision boundary that is way too precise for the kind of data that we have, and its shape is very blocky, and it's just not a sensible region. So this is an example of the kind of overfitting that a decision tree algorithm might exhibit. And we can look at this further by looking at how trees can overfit the data. And we can look at it from a high variance perspective. So recall that in the previous video, I defined what is high variance. I defined what it means for an algorithm to be high variance. And we say that of an algorithm if it overfits the data and small perturbations of the training set result in big changes of the predictive model that it outputs. So overfitting and high variance are synonyms, but high variance in addition highlights the fact that small perturbations to the training set will cause big fluctuations in the predictive model. And one way in which we can visualize this is by taking random subsets of the data and training a different decision tree model on them. So here I am taking samples of 40 data points. So I'm taking 40 data points uniformly at random, and I am training a different decision tree on each of them. And you can see that each of these decision trees returns a partition that is completely different, and this is a dramatic example of the high variance problem. If we change the data set a little bit, or if we make changes to the data set that still have, here we still have the right structure, we still have enough, we should still be able to separate the blue and the other 2 classes, but still these changes in the data set, they create completely different predictions. So random forests are a way of addressing this overfitting and high variance problem using the technique of bagging, which we have seen earlier. And a random forest is nothing but a bagged decision tree, or it's an ensemble of bagged decision trees. So it is bagging applied to a decision tree model. If we were to instantiate our example with bagging, this is what we have, and I have just replaced the earlier definition of bagging by using decision tree as the model here. And random forests are really easy to implement, just as bagging is easy to implement. This is essentially Python code that closely mirrors the pseudocode that I had in my earlier slide. Now, let's see what happens if we now run these random forests on the flower dataset. So I have trained earlier in one of the earlier slides, there was a cell in which I implemented random forests. Training that creates a set of models, and now I can visualize their predictions on the flower dataset. In visualizing their predictions, I can go back here and I can look at So here we have 300 models, and each of them is sampling only 10 data points. So here I have the average of 300 models, and each of them is trained on 10 random data points in the data. And now if I visualize this, I have a decision boundary that is much smoother than what I had before, and it looks much more natural. Here, this kind of smooth curve is something that we would expect, and here also I have a smooth curve between the two classes. It's not as jaggy anymore, which is good. And also it clearly overfits the data much less. This decision boundary is much more intuitive, and it's no longer trying to put this one data point in its own class. This set of predictions is just much better behaved, it generalizes better, and is just a more intuitive looking boundary. So to summarize, we defined random forests as a new kind of algorithm, and because it's built on decision trees, it still can solve the regression classification problems, and because it uses this, because it is simply bagging obtain train on top of decision trees, our model family is still based on decision trees, and our objective and optimizer is the same that we used for the decision trees. So what are the pros and cons of random forests relative to other algorithms? Since they're based on decision trees, they still retain a lot of important benefits that decision trees have. They don't require any scaling of the input, they handle continuous and discrete features equally well, and they work equally well for classification and regression without modifying, without really making a lot of changes to the algorithm. And unlike decision trees, they are in practice quite often accurate. And so random forests are a very competitive class of algorithms, and on many benchmarks that compare classical machine learning algorithms, random forests are they perform quite well. On Kaggle competitions, random forests are a competitive model. Now, their disadvantages is that because they are bagging a large set of decision trees, they lose a lot of the advantages that these decision trees have in terms of interpretability. So if we bootstrap together 300 decision trees, even though each decision tree might be interpretable, the average of 300 decision trees is no longer interpretable. And finally, decision trees work, even though they're accurate models, they typically work better with features that have been pre-processed. And if we're working with some kind of raw, unstructured modality such as images and audio, random forests would not work as well.